We went meta here. All right. So I'm very happy to introduce actually the last talk of the conference that is a proposal that was accepted by the program committee. So Harish, you're going to talk to us about PriDe. I don't know what PriDe contains, but I can't wait to find out.
Perfect. So going back to the segue, the funniest joke I think in Zero Knowledge was my mom. She asked me what I was working on, and I said Zero Knowledge, and she said, I can see why. So I think Indian moms and their cutting humor can have long-lasting impact. But moving on to my other joke, this is a disclaimer that I was forced to make, lest anything I say makes the world economic order crumble, the Dow goes down, S&P 500 goes down. So it's purely my own opinion. Nothing I say goes back to JP Morgan, which comes back to my previous slide, which is joint work with Uwe and Antigone, who are basically with JP Morgan AI Research, and Chadi, who's at the blockchain team of JP Morgan. So private, decentralized, confidential transactions. So that's what the mystery is solved. PriDe stands for private, decentralized. So what is our focus? As I said, private. We want privacy where identity of the parties are hidden. We want decentralized because we wanted to be working with the JP Morgan blockchain team, who came to us with the problem. So we really couldn't do away with the decentralized part. The account-based model, because again, JP Morgan blockchain team was running it on an Ethereum-based blockchain, so it's made sense, account-based model. Confidential, we want the payload of transactions to be hidden. Batchability is, as unintuitive as it sounds, JP Morgan can be altruistic. Yes, we are batching transactions together. Yes, we lose the revenue from the fees, but nonetheless, it's okay to do some good from time to time. Hopefully, well, the slides, we need to edit it. We need to post-process the jokes out, lest I lose my job. And concurrent, we want some competing transactions to proceed. And forward secrecy is a cool idea that's very much part of the norm in any secure messaging platform, where you want past transactions to be private, even if you get compromised right now. The question is, what does it mean for forward secrecy in the context of a blockchain, which is supposed to be an unimmutable, time-pervading ledger of all transactions? So this is roughly the focus. So this is our approach, which is not really, we build on prior work. We use encrypted balances. So every balance or a payload is sort of encrypted under a public key. So it's a public key crypto system in essence. And then we want to transfer payload. When that happens, what I do is I choose a bunch of receivers. And this is where we depart from previous work, is any number of them can be decoyed. The idea behind all of these dummy users set is that some of them are zero, some of them are non-zero. You really don't know who is the intended recipient. And the payload is encrypted under the respective public key. And then the balance, you just use some homomorphism, and it works. Now, we want the malicious behavior to be prevented because everything happens under the hood of encryption. We do need zero-knowledge proofs, and that's where I come in with this talk, because we do use zero-knowledge proofs to prove that what we do, the sender actually behaves properly. So functionalities, this is how we register a contract. We just say, hey, this is my public key, do the registration, thank you, smart contract. And then here, critically, we can, because this is the start of the process, we don't need any randomness. So the smart contract runs a pretty much deterministic process, which is I encrypt 0 under the public key with randomness 0. Funding an account is where I'll say take it from my Ethereum wallet and then put the money into my account. Again, I can do with randomness 0, which makes life easier. And then burning an account is saying, hey, I'm done with PriDe CT. Let me pull my money out of it. So I need to prove that I am the owner of the account, and I know what the balance was. And then the smart contract simply updates the balance to 0. And finally, this is the cool part, is transferring of accounts, where I'll say these are my set of public keys. And I will encrypt the payload under the public key, and I'll do some proof. So what do I need to prove? Obviously, I need to prove that I am the owner of the account, that law of conservation of money holds good, what goes in comes out. And then eventually, I need to prove that the payload is zero because we work over field arithmetic, which means negative and plus you need to really distinguish. So this is where range proof actually comes in. And prior work is Zther, which started this entire thing in I think in Financial Crypto in 2020, where they said, they proposed a solution which said, end users, n minus 2 of them are decoy, 2 of them, 1 of them sender, 1 of them receiver. So then they had a vector for sender and a vector for receiver, where exactly 1 position of the n bit vector was 1. So you could use 2 1 out of n proofs, blah, 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 and then it was very informal. Anonymous Ether, which came out after, which was in S&P 2023, or maybe 2021, actually, said there were some issues with Zeta. So what it said was, let me introduce a new proof protocol, which is to say that any number of n can be non-zero. Specifically for the use case, they only could do it with, for n, let's say, 2 non-zero entries, because they really needed the constant, because otherwise the asymptotic costs ran to n log n squared, n log squared n. Okay? So this is where we are at, and this is where we come in. Oh, I guess I missed a slide that didn't get copied. But the rough idea here was that to get sender anonymity is actually moot point because of the way a smart contract works, is that oftentimes the person who's invoking the smart contract is the sender. So you trivially attack sender anonymity. So that brings us to the question, let's sacrifice sender anonymity, and what all can we get? Okay, and this is where we get batchability, we get some concurrency, and we also get this idea of what forward secrecy means. So now I'm going on to show the, just a theoretical, or rather a run of a protocol. So if I didn't have privacy, it works easily, but I'll say, I want to send Bob 10 and Charlie 20 and blah, blah, blah. Everything goes through, and then then the blockchain confirms it, so it debits the money and credits it to the respective users. Well and good. So now how do we work with PriDe? This first, I compile and deploy the smart contract, and then everyone has to register. So where now everyone's balance is now 0 locked under their respective public keys. And then I would say deposit from my public wallet 100, so deposit 80 from it. So now it became 80, in case you didn't notice. And then now I would just say, these are my dummy users, some of them are non-zero, some of them are 0, post it. Make the magic. And it does. So it does this, all while I prove the zero knowledge that everything is conserved. And Bob wants to say, I'm done. Give me back my money. So it just withdraws. Okay? So the punchline of this is that if you really take a look at what anonymous Ether does, it's that it critically requires 2 out of n to be non-zero. And therefore, if I were to do this for multiple transactions, I really need to do this that many times. So what we did was we ran both anonymous Ether and PriDe, and we just took a ratio to say how much batchability do we need to make this a viable construction. And we said that basically if I batch it, so take 32 receivers, even if 7 out of the 32 receivers are intended recipients, it's much better than naively running 7 times anonymous Ether. Okay? Now, there are some ongoing works which I really want to plug in here, which is flash proofs, which is like this cool way of improving bulletproof. I do summarize it in just next slide, which seems to be more efficient in terms of gas consumption, because the verification is where they really make gains. So this is what we predict would happen. But the caveat is that you lose any amount of efficiency that you get from aggregating proofs, because they really need to just run linearly. There's no aggregation that saves proof size. So their approach is to basically break down this value into binary decomposition, and then essentially generate this L by K matrix, where each value is either 0, the W underscore I is either 0 or an exponent of 2, right? So now what I will do is I will just collapse it down a row vector. So I'll just literally add across columns. I'll just reduce it to 1 row vector. And what the prover needs to prove is that the summation of this modified row vector is essentially what you are proving. So it's much faster, that they show that faster both in terms of concrete numbers from proving size and also from gas consumption. They implemented on a solidity concept. And then there's another work that just was in S&P this year, where they use a different kind of range proof, where they say that you don't need to pad. If you don't want to pad, you don't need to pad, and you get better performance than padding with bulletproof. And they show this for Monero. So they don't have a solidity code, and we have to implement the solidity code, which can be a pain in its wrong place. So that's another ongoing work which we put a pin in it, but first we want to do this flash proof. And there are some interesting theoretical questions that come out of it that I'm happy to discuss. And then final piece of the puzzle is this forward security. So when we submitted this paper, as you submit it, you get rejected a bunch of times. That's the work. But then they come up with these kind of, this hacky solution towards forward secrecy. One might argue that ours is also a hacky solution, but I'm going to claim it's not. So they said, OK, have the sender just create a new public key secret key from time to time. But then when do I need to delete it? When do I need to create a new one? When do I tell people that I've created a new one? So it becomes a circuitous problem. So therefore, what we wanted to do is to use some literature from secure group messaging, which is that instead of the sender will help the key of the receiver evolve. Right? So this is something that's very popular, using a primitive known as updatable public key encryption. So if you use any secure group messaging, the group messaging working group from IETF, they have this proposal to use updatable public key encryption. Different from updatable encryption, in case you know that whole rabbit hole. But the idea is that now I will give you the randomness with which you update the your key. But I need to prove some stronger security because I am controlling the process, so I can easily mount a denial of service attack. So that's where we need to prove that not only is regular LGMAL vanilla, LGMAL is a secure UPKE, you also need to prove that it's secure under stronger security definitions. Now, that's it. I'm happy to go over any slide. I do have a tendency to speak fast, but I got more jokes if you want to hear it. But otherwise, thank you for your attention.
Any questions, anyone?
One last plugin. If you're in Zurich, you will hear the same talk again tomorrow. So this is third day in a row where I'm presenting the same talk.
So the security model of the key evolution, is your forward security dependent on who sends to you?
No, so as long as there is one good sender who has sent it to you in a particular epoch and your key evolves, you have done the evolution, then you're good. Which is kind of the idea in which pretty much FSPKE also works, is that there are keys concurrently being evolved. As long as your secret key has evolved, your public key, you're good with the old transactions. So that's the model. So here, as long as there's one good sender who is participating in the transaction, you're secure.
Yeah. And I guess if you don't get any payments within a period, you can send to yourself.
Yes, exactly. You can also do the refresh yourself. The only thing is that the benefit here is that the sender can just keep updating the public key state, which is critical because you want the public key to be updated. At the same time, you want the continuity of the transaction after the public key. Even if the receiver hasn't caught up yet, you want the receiver, when it catches up, to have consistent state.
More questions? I have a question.
Go ahead.
Do you see a path where some of these techniques would be applied in your line of work?
Oh, as in specifically as a banker?
As a center of excellence, AlgoCrypt AI research, JP Morgan.
Okay, let me give you the back spiel. So this was actually something that was much needed because JP Morgan blockchain team was originally using Tessera as a transaction manager. This is from Consensus Quorum. And the idea there was that if I want privacy, you and I will talk a side channel. We will do all kinds of nonsense. And then we will put a transaction posting in our private, Tessera, hence the name. And then no one can verify it. So what they got was brilliant private transactions, but you lost public consensus. So that's why they came to us. And Anonymous Ether was also something that was developed from JP Morgan AI Research. Ben Diamond was on our team. But then the cost of it was really not worth it. But having said all of this, I do believe that I've been told that there's been a pivot from the business side to not go for in-house solutions. But they might be finding it better to just go for an external vendor for whatever reason that I don't want to have it be recorded for posterity's sake.
No problem. You can go and chop
You can
any part.
sidebar, yes.
Just so to add to that, actually at some point both Zcash and Kedit were in conversations with JP Morgan about adding zero-knowledge proof asset transfers to the Quorum blockchain way back. And I'm happy to see that these considerations are coming back.
Yeah, I actually refused to work on that project because well, JP Morgan, but the specific reason was that they wanted shielded issuance, and so it would have been impossible to prevent the issuer from inflating the currency. So I objected to that, and unfortunately, ECC is great. If you object to a particular project, then you can just not work on it, and that's normalized within ECC.
All right.
Okay.
More questions or comments or reminiscence of past interactions with a bank? Okay, thank you very much.
Yeah, you can ask me any questions off camera.
Okay, perfect. Thank you.